Hello, everybody. My name is Jacary Sapp, and I'm going to be talking about doped manganite thin films, stored as random alloys and superlattices by molecular beam epitaxy. Let's get straight into it. Now, I work in the A-LEGO lab. It's actually right down the hall over there, with Dr. Maitri right over there. It stands for the Atomically Layered Epitaxial Growth of Oxides Laboratory. My specific major deals in material science, materials physics. And this laboratory is an experimental condensed matter physics laboratory. Very complicated, a lot of big moving parts. You can see one of our giant machines right over there. I love dealing with it. It's become my baby at this point. We specialize in synthesizing and studying perovskite phase thin films, and we'll get into what that means later. But we grow many different types of films. We grow cuprates, we grow vanidates, we grow manganites, which is what we'll be focusing on for this presentation specifically. I've grown a lot of cuprates. Cuprates are cool, they're superconductors. And here are some of the current members, including myself. Some of the other ones are also in the group, and also in the presentation here today. And some of the past members, including Caitlin, James, and Dakota, I'm piggybacking off of some of their work. And this is an extension of specifically one of these papers by James Payne right here that I'm going to be expounding upon. Now, first, let's get into the chemical properties of lanthanum, strontium, and manganese, since those are going to be mainly the parent compounds for what we're going to be using here. So, lanthanum has an oxidation state of +3, just, usually, as you look on the periodic table. Strontium +2, manganese can occupy different types of oxidation states since it's a transition metal. Lanthanum is a lanthanide material. Strontium is an alkaline earth metal, meaning it has a generally defined oxidation state. And when you combine these into a perovskite phase, which we'll get into that in the next part, you get these different types of structures. Lanthanum manganese oxide, strontium manganese oxide, and lanthanum strontium manganese oxide. Now, lanthanum manganese oxide is a mud insulator, and it's a really well-studied anti-ferromagnetic material, and it has this following electron configuration, T2G3 Eg1. We'll get into what that means a little later. Same with strontium manganese oxide, except it's a band insulator with this electron configuration. And lanthanum strontium manganese oxide is the interesting one. This is the parent compound that we're going to be piggybacking off of for the rest of this presentation. It essentially is just a combination of lanthanum strontium, or lanthanum manganese oxide, and strontium manganese oxide. You mix these two, some ratio of the two of them defined by this X number right here, telling you how much strontium is in your system versus how much lanthanum is in your system. And this is also a really well-studied material. You can tune between the anti-ferromagnetic and the ferromagnetic states, judging based off of how much of that strontium doping you're putting into the material. And this is a perovskite, this crystal structure right here. Now, in these crystal structures, specifically for manganese usually occupies the B site, which is this little one right here, the little blue one in the center. And lanthanum or strontium typically occupies the A sites, these big green ones right here. And the little orange ones are just oxygen atoms. This is just a little phase diagram of lanthanum strontium manganese oxide depending on temperature and the strontium concentrations. This is again showing that when you change the strontium concentration, this X number, you can tune between different ground states of the material. Now this is just a better showing of what a perovskite looks like. On the left right here, this is specifically on a strontium titanate substrate. You can see 3 layers of a manganese oxide, which in this case would either be lanthanum or strontium manganese oxide. But the point is, this is just a better visualization of the materials that we're growing. On the right, this was actually made by one of our former group members, Nathan. This is an array of perovskite thin films. You can imagine this is what one layer of these atomic lattices look like. And on the left right here, this is what they would look like when they're stacked on top of each other. We can grow these single atomic layer by single atomic layer to however much we want to get a certain thickness of a thin film. Keep in mind though that these films are incredibly small. Like one of these unit cells are about 4 angstroms thick. And if you don't know, an angstrom is 1 × 10⁻10 meters. So incredibly small, way too small for your eye to see. Now, touching on this real quick. The octahedral field splitting, that's where that whole T2G and EG thing comes in. You can have a metal center, like a manganese atom, which has 5 well-defined d orbitals, all of the same energy. Now, though, if you stick these oxygen atoms or another source of negative charge around them in this sort of way, where you have 1 on top, 1 on bottom, and 4 in a square, like planar configuration around that, it leads to this thing called field splitting, where now instead of those 5 d orbitals occupying the same energy, now they occupy different energy levels. 3 of them have a little bit of lower energy, and 2 of them have a higher energy. This can change depending on how the molecule is arranged. This is just specifically for an octahedral structure. But the important part to take from these is this is what drives a lot of the interesting magnetic and electric properties within these materials, tuning between these states right here. Now, what this study is focusing on specifically is the addition of europium into these samples. So now, instead of just lanthanum, strontium, and manganese, now it's going to be lanthanum, strontium, europium, and manganese. Europium has an oxidation state of usually +3 or +2, and it's also a lanthanide. However, unlike lanthanum, which does not have F electrons, europium does have F electrons. I believe it has 7 specifically in the 4F orbital. And the whole purpose of this study is just to understand what's happening when we throw these europium atoms into this crystal structure. And it leads to this following configuration here, which we can see here. Again, it's a perovskite phase, but now the point is, instead of it just being a mix of lanthanum manganese oxide and strontium manganese oxide, now it's a mix of lanthanum manganese oxide, strontium manganese oxide, and europium manganese oxide, leading to this configuration right here, where not only do we have this X that we still have to worry about, now we have this Y, defining how much europium we're putting into these materials. Where europium also, just like lanthanum and strontium, occupies these B sites, and manganese continues to occupy the A site. And we can grow these in different ways. Using molecular beam epitaxy, we can grow these as either a random alloy or a superlattice. Now, what do those mean? On the left here, you can see a random alloy, where these lanthanum, I'm just like LMO, SMO, and EMO, where these different structures can be randomly dispersed throughout the material. You can have a layer just randomly comprised of LMO, SMO, and EMO with no type of ordering whatsoever, as defined by this picture right here. But we can also grow them as superlattices, where we specifically give it some ordering. So if you see here, this would be a layer of europium manganese oxide, a layer of lanthanum manganese oxide, and a layer of strontium manganese oxide. This effectively changes what we define as the unit cell, right? Because how we define unit cells in crystal structures is the shortest repeating pattern of the material. So for a random alloy, the shortest repeating pattern is just one of these, which is approximately 4 angstroms. But for a superlattice, now the shortest repeating pattern is this whole system, this 3 right here, which is approximately 12 angstroms. So these are different ways that we can grow these materials. And now we're trying to find out how does the electric and magnetic properties of these materials change as we not only add europium, but also change the ordering of these materials, how we stack them. So I've talked about MBE a lot. We grow these films using molecular beam epitaxy, but what actually is it? It is a physical vapor deposition technique wherein we get sources like elemental sources, usually metals. We heat them up to incredibly high temperatures. Some can be a couple hundred degrees Celsius, some can be over 1,000 degrees Celsius. And you get a beam of atoms that can flow off of these materials via just sublimation, just the atoms going immediately from a solid phase to a gaseous phase. And we have physical shutters that block the flow of these atoms. We can control when and how much atoms we throw down onto a substrate, which is just a template, essentially just a template crystal. Now, we're still concerned with this chemical formula here, this lanthanum 1 minus Y, europium Y, 1 minus X, strontium X, MnO3. So this is telling us how much europium versus how much strontium versus how much manganese we're throwing down into the system. And we can control all of these via molecular beam epitaxy. That leads to these really phase pure atomically flat crystal structures. And we're going to specifically study these using READ, which is an in situ growth measurement, or characterization measurement, which we'll get to in the next slide. We're going to be looking at some X-ray diffraction data and some resistivity measurements. But these are the 4 samples that we're going to focus on specifically for this study, where we held X to be 1/3 constantly throughout the material. So in each of these samples, there is approximately 1/3 of the material is strontium manganese oxide. But we're switching this Y to be from 0 to 1/2. So half of those lanthanum sites, those what would be lanthanum sites, are now going to be switched with europium in 2 of these samples. And they're also, 2 of them are grown as random alloys, where they're just randomly dispersed throughout the material, and 2 of them are grown as superlattices, where they're specifically ordered throughout the material. And you can see a cross comparison over here, where these 2, the ordering is the thing that's changing. So these 2 right here being random alloys and these 2 being superlattices, where the europium is kept the same. These 2 do not have europium, these 2 do have europium. And going in this direction, europium content is the thing that's changing. So yeah, europium content is the thing that's changing. So this does not have europium, this does. And this does not have europium, this does. However, the ordering is being kept the same. So these 2 on top are both random alloys, and these 2 on the bottom are both superlattices. You can see that outlined by these right here. And we're going to be talking about these specific four films that we grew for the rest of this presentation. Now, first, let's look at some read data. Read is a really cool technique that we can use within molecular beam epitaxy. It's an in situ characterization measurement that essentially tells us how good is the crystal that we're growing. Because obviously, if you throw down stuff, it can form whatever it wants, right? We can't dictate what it forms, but we can give it the conditions to form what we want it to form. And read is the thing that tells us, are we forming the thing that we think we're forming? So a good read structure or a good read image like these right here, you want it to be characterized by long bright streaks, no other streaks like present anywhere else in these. So like these well-defined order streaks where this is the 0th order, this is the 1st order, 2nd order, all that stuff. This is what you want to see in a good crystal structure. This is telling us that you have a material that is repeating and that is atomically flat and that it is pure, i.e. like there's no other second phases being nucleated throughout the material. Essentially, we just have an electron gun built into the chamber, a little tungsten filament, we apply voltage to it. You get electrons, they shoot out at the substrate at a really glancing angle. Then you can survey about the first 1 or 2 layers of the material so that we can see, are these layers growing what we think we're growing? And judging based off of these read images taken at the end of each growth in these specific crystalline directions, they tell us that yes, we are growing phase pure perovskite thin films. This is exactly what you want to see for a material such as this. And now some X-ray diffraction data. So for random alloys, or for one of the random alloy samples, that's going to be representative of both the random alloy samples here. Going back to this picture like here, a little cutout of this picture. Remember this, from here to here, 1 unit cell is defined as approximately 4 angstroms. So we can use X-ray diffraction data to, again, tell us, are we growing what we, or well, by the time we use X-ray diffraction data, that's telling us, did we grow what we think we grew? And since we have, you can see these peaks right here, these 4 peaks. Now these peaks are defined as the substrate peaks, the peaks that the material that was grown on, which in this case was neodymium gallium, NGO. And you don't see any peaks resulting from the actual film itself. That's because the film peaks align with the substrate peaks. They're just incredibly close to each other to the point where you can't differentiate them. And that's actually a good thing. That's what we want to see for these types of materials. That tells you that not only is the film commensurately strained to the substrate itself, but the lattice matching between the substrate and the material itself is incredibly close. That means that we grew a perovskite phase crystal just like we wanted to grow. However, switching over to the super. Isn't it? Oh. Now going. There we go. Okay, now going over to the superlattice material. It's going to be a bit different in X-ray diffraction data because we have these unit cells that are now extended from being, instead of 4 angstroms, now we have 12 angstroms. Because when you're dealing with X-ray diffraction data, when you're dealing with read, you have to focus on this thing called reciprocal space, which is essentially just inverse space. So in real space, you have meters, right? We can define some physical length. However, when you're focusing on inverse space, now you're looking at 1/meters. Yep. So this is defining why you see all these extra peaks here in these 2 superlattice samples that are not present here in the random alloy sample. Because we have a longer unit cell, that means now we're going to have more repeating points in the XRD data. A longer repetition in space equals a shorter repetition in inverse space. That's essentially what this is telling us. That's why you see only 4 peaks here. However, you see triple the amount of peaks here because this is triple the length that this is. That's essentially what this XRD data is telling us. It's just telling us that we grew a phase pure perovskite thin film. And if we didn't, we would see extra peaks defined by other structures. Now, electronic transport data. This is essentially just telling us the electrical response of these signals. All we do is we get some fingers, some metal fingers, we attach them to the top of the samples, either in a line measurement like this or in a 4-corner measurement like this. I've gotten really good at these, I've done it a lot. And we measured the resistivity of these samples or the resistance between the fingers. And this tells us we shoot a current through the material from these 2 prongs right here to the 2 current prongs and measure a responding voltage. And obviously that voltage response is going to be in part from the film itself. So this is telling us the electrical response from these films due to an external current. And we can measure these as a function of temperature. So these right here are the 4 plots acquired from these specific 4 graphs, or from these specific 4 films, the electrical response of these signals, showing us how does it act electrically as you cool it down. And in this sample right here, the LSMO, the regular LSMO sample, the regular random alloy, you can see this right here, this turn right here. This is what's called a metal insulator transition. It goes from being an insulating material to being a metallic material. As you cool it down, the resistance goes lower, which means the resistivity goes lower because those two values are directly proportional. And same for right here, except now this metal insulator transition has just been knocked down to about 120 Kelvin as opposed to the about 330 Kelvin right here. In the superlattices, though, you see something a little differently. In this one superlattice over here with europium present in it, it has an insulating state down to a point where we can't measure it anymore because the film is too resistive. However, in the superlattice of just the regular LMO, SMO, the regular lanthanum, strontium, manganese oxide, it has a metallic state as you cool it down. The more you cool it down, the less resistive it gets. And we just find the resistance using Ohm's law. Nothing too complicated. Now, this is a paint a clearer distinction between them, just because the last slide doesn't really show the distinction as good as this one does. So, focusing on these two up here, again, these turning points right here, those define your metal insulator transitions, and I made this graph specifically to show how the metal insulator transition gets knocked down by a significant amount in temperature as you add this europium. Because remember, europium is the thing that's being changed as you go this way. So again, going this way in the superlattice point, you get a metallic state versus an insulating state. Again, drastic change. Now going down where the ordering is being kept, or where the what? Yeah, where the europium is being kept constant, and the ordering is the thing that's being changed. So these two being random alloys, these two being superlattices. As you go down, you see that this metal insulator transition that was present in the regular LSMO random alloy, it's not in the temperature range that we measured for the superlattice equivalent to that. However, in the other one, in the one with europium present in it, where half of those lanthanum sites were subbed with europium, now we've got this metal insulator transition that's present in the random alloy. However, in the superlattice, it's nowhere to be found. In fact, it's just a completely insulating state down to the point where we can't measure it anymore. So again, a significant difference that's highlighted by this plot specifically right here. And there's a lot more stuff that we plan to do with this type of research. We want to get squid magnetometer measurements done. Actually, those are being currently done by Dr. Carrot right now. And we want to get spectroscopy measurements done to further understand how these F electrons are influencing the material, the europium. And we want theoretical work to be done so we can understand the density of states within these materials a little better, understand how these F electrons in the europium is changing the material itself, or altering its properties in some way, either the magnetic properties, electrical properties, or optical properties. So we can probe all those with these different types of measurements. And that's all I have. Now, obviously, I worked in Dr. Maitre's lab. Thank you, Dr. Maitre. It's been great. And a lot of these, 3 of these films specifically, and the XRD data was done at a Paradigm laboratory up in Cornell, which I actually got to go there last summer. It was very much fun. And the A-Lego team, thank you, guys. The physics department, it's been great. I've loved doing this for the past 2-3 years. And that's it for me. I'm done.